Hello, I am Dr. Kyoung-Hee Kim, a professor of architecture and director of the Integrated Design Research Lab at UNC Charlotte. In this lecture, I will provide an overview of the importance and design principles of sustainable building enclosures. Sustainable building facades serve multiple functions and operate across different scales and applications. The building facade is not just an aesthetical surface, it is a high-performance interface between the indoors and outdoors. In fact, as architects Zaira Polo and Anderson argue, the building facade's significance lies in its material performance in response to economic, technological, and environmental demands, less in superficial ornamentation. As I mentioned earlier, building enclosures operate at multiple scales from people to cities to the planet. They can function as economic, environmental, and social infrastructure, and they are more than a mere building surface or an aesthetic element. They interact with the environment to the advantage of people inside the building, the surrounding community, and the planet. On a personal level, the building enclosure is a filter against excessive outdoor environments. The sustainable building envelope promotes a healthier workspace by providing clean, well-ventilated indoor air and daylight illumination, contributing to overall well-being and productivity. At the building and community levels, in addition to offering quality protection, the building enclosure enhances building energy efficiency and longevity. Moreover, it can capture clean energy and mitigate or collect stormwater runoff, making the urban environment more sustainable. On a global scale, it reduces energy consumption, carbon emissions, resource consumption, and the cost of operating energy-driven buildings. It can integrate clean energy for on-site power production. It also has the potential to include living biofacades to foster biodiversity corridors in urbanized zones. In this planetary sense, the building envelope becomes a tool to align architecture with the Earth's ecological needs. Another theoretical framework is to understand how building components and systems adapt over time, as explained in Stewart Brand's concept of shearing layers of change. Brand describes that buildings are composed of architectural layers with different lifespans. The site layer is essentially eternal. It provides the geographic foundation and context for the building, which all other layers of a building are built upon. It also influences the building's physical, ecological, social, and economic relationships with its surrounding environment. The structure might endure for 30 to 300 years, as it's costly and difficult to change. It provides the essential building's bones, ensuring safety and stability over time. Moving inward, the skin, the building enclosure, typically changes roughly every 20 years or so to keep up with technological advancement and aesthetic appeal. The building services such as IT, MEP, HVAC, etc. wear out and require replacement every 7-15 years. They are crucial for operating buildings to ensure occupants' comfort, health, and well-being. The space plan, such as interior layout of walls, partitions, and finishes, might be altered on the order of every 3 years in a commercial setting. It allows for flexibility in spatial alterations, adapting to the evolving needs of occupants and activities. At the most changing layer, the stuff inside, such as furniture and equipment, can change even more frequently, sometimes daily. The key idea is that each layer shears at its own pace. The building changes into pieces rather than all at once. This layered approach is part of systems thinking. Faster changing layers like services or enclosure systems should not be impeded by slower ones like structure. Sustainable design must account for continuous upgrade by allowing layers to be updated without disrupting others. Another design principle that Brand's theory promotes is adaptability within each layer. Adaptability means designing each layer for ease of assembly and disassembly. Using modular systems and mechanical connections, for example, is a good approach as they can be easily disassembled and assembled with future technologies required for upgrades. Let's shift our focus to the multifunctionality of sustainable building envelopes. We'll use 3 functional categories: protect, promote, and regenerate. Protect refers to the facade's fundamental role as a shield safeguarding the building and its occupants against weather and outside threats. It should maintain its strength and rigidity while enduring the wind, seismic loads, and other external loadings that could threaten structural integrity and serviceability. Beyond structural integrity performance, energy management is also an essential attribute because the facade is the primary interface with the outdoor environment and controls solar gain, heat flow, and air filtration across various seasons. Another critical protection is weatherproofing against rain and moisture because water leaks and condensation cause molds that threaten occupant health and material longevity. In line with structural integrity earlier, building enclosures should be able to withstand impact from storm debris, collisions, or even special hazard scenarios such as blast resistance. Another level of protection is that building enclosures should provide life safety features such as fire resistance and the containment of smoke spread, protecting occupants during fire-related emergencies. Additionally, building facades can be designed to block unwanted noise from outside, and their acoustic performance is rated by Outdoor-Indoor Transmission Class, OITC. Building enclosures can be part of protecting nature. They can be designed to prevent bird collisions and to avoid disorienting sea turtles for nature protection. Certain buildings with a history of bombings, embassies, and government buildings may require enclosures designed to resist explosions or provide blast protection. All these measures ensure the safety of users and nature, as well as the longevity of the building. In short, the building facade is an essential architectural element, serving as the first line of defense against environmental stresses and hazardous threats. Let's move to the next functional category of the promote. The promote covers how the building enclosure further enhances the indoor environment and occupant health and well-being. Sustainable facades promote good indoor environmental quality, IEQ, in terms of thermal comfort, daylighting quality, air quality, and user experience. For instance, they filter excessive solar gains and mitigate cold bridging to provide a thermally comfortable space. They also allow ample daylight inside while controlling glare through features like well-designed windows, light shelves, or shading devices. They also provide occupants with a view out to connect them with the outdoors, which has known benefits for wellness. The facade can contribute to fresh air and natural cooling by enabling natural ventilation through operable windows or ventilation panels. Next, the aesthetics and even biophilic qualities of the facade also play a role in work productivity and less sick leaves. These design features include natural materials, green walls, or patterns inspired by nature. They can reduce stress and improve the emotional experience of space. In essence, under promote, the facade isn't just minimizing negatives, it's actively creating a healthy, pleasant environment for people inside. All of this improves occupant health and well-being. Regenerate is the third functional category that highlights the facade's capacity to actively improve or regenerate resources and aspects of the ecosystem. Traditional high-performance enclosures aim for neutrality, aiming to do no harm, but regenerative design often aims for resource generation and a positive impact. As the building's direct interface with the outdoors, facades can generate renewable energy, for example, by integrating photovoltaic panels. A solar facade can harvest energy from sunlight, turning the building's skin into a small power plant and reducing the building's reliance on fossil fuels. While energy production is one form of regeneration, building facades can serve as vertical landscapes where the integration of nature supports carbon sequestration and air purification. Supporting biodiversity is another regenerative quality, along with water regeneration through rainwater collection and filtration systems embedded in the facade. Facades can capture rainwater for domestic use and irrigation. All these approaches assist the building not only to lessen its footprint, but also to enhance the entire ecosystem. In conclusion, sustainable facades play a vital role in building performance by supporting operational efficiency, occupant health and well-being, and the regeneration of surrounding ecosystems. In essence, the facade is central to realizing a regenerative and resilient built environment. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in sustainable architecture and its role in shaping future cities.